Well, yep. Thank you, everybody, to be here this afternoon in an afternoon session after lunch in a warm room. So I highly appreciate your presence here. I was here for the first time 3 years ago, and I was presenting InSAR Interferometry, which is a technology that provides with very precise measurement of the surface anywhere in the world, in planet Earth. I put it in the context of the civil engineering industry, and I spoke about the advantages and disadvantages of this technology. It's good that during the conference we have already heard a few people talking about it. Yesterday was the CSIC with Sakthi. She was talking about the use of InSAR interferometry from the perspective of structural engineering in the Waterloo Bridge monitoring. This morning it was Peter from Sensiv talking a little bit about the integration of InSAR interferometry with wireless in-situ instrumentation data. So the title is Integration for Regional and Asset Satellite Observations for Assessment of Infrastructure Resilience. Sounds a little bit complicated, but at the end of the day, this is the roadmap for Telespazio Vega in terms of InSAR interferometry and an asset assessment. And that is going to be explained in the context of two projects, one performed with Innovate UK, and another one which started to move on about 6 months ago, and it's a H2020 EC project called 4C. Actually, I don't have the thing to pass the... Sorry, I don't have it in my hand. Yes. So let's just talk a little bit about resilience. Resilience is a huge word, it's a huge concept, and I'm going to be talking about the more than resilience, the physical robustness of assets for infrastructures. So assets studied in isolation give an incomplete view of resilience. It is only when asset condition analysis is integrated with its environment that the full dynamics of the infrastructure comes to life. So we cannot just only look at the infrastructure, but we need to look at the surroundings as well, providing improvements for infrastructure resilient assessment. How to do that? I mean, I get also in another kind of big concept, which is the digital twin. So basically, us as providers of digital satellite-derived digital data are trying to move towards the digital twin in order to have a representation of the reality in the digital world that allows us to analyze the data, to interrogate the data, and eventually to make some predictions or intelligent decisions. So that's how we came up 2 years ago with satellite structural health monitoring system. It is a tool we have developed at Telespazio. It's an algorithm that allows to put the position of the InSAR point cloud data, because that's what we generate, point cloud data, into the asset, specifically where it is. So it will allow us to, once it is in the 3D environment, to analyze the full movement itself within, or the deformation within the asset. So we started with a little bit of an analysis of satellite health monitoring, what the problems are for the end users, for clients and contractors. So we didn't really decide to do this on our own. It was a collaboration with end users like TfL and EDF. So the asset managers required reliable and long-term monitoring and assessment of their assets, performance and condition, particularly to schedule maintenance, ensuring maximum utilization and longevity of their assets, and at a minimum downtime. A broader understanding of the relationship of the assets in the ecosystem. I'm talking about getting the asset from the digital environment and extrapolate it into the rest of the environment, which is the GIS environment, the terrain environment that is affecting directly the asset or the infrastructure. Integral visualization of the asset health, as I was explaining before. So we have a visualizer in order to be able to get grip of what's happening within the asset. And eventually, that's going to be our next step, which will be developing the H2020 4C project, which is to be able to make some predictions and to raise some alerts. So this is developed with satellite data. That doesn't mean that it can only be done with satellite data. this is the beginning, and we would like and invite within the 4C project, for example, the end users, the clients, to integrate the in-situ instrumentation to make the models more intelligent. So we go from, as the title said, from regional studies of surface deformation, like for example this valley. This is a valley in Italy, and there is a quite important motorway running through it. And straight away with the point cloud deformation data, you can spot where the areas of deformation are. So then with that information, you can be more specific, downsize and go to the next scale, which is to look at the details of the point cloud data, and in order to be able to relate the position of every deformation point into the specific asset. So this is our data input for the tool. So as I said, well, okay, SSHM, from the concept to the tool was part of the Innovate UK study. We worked with University of Salford, with TfL and with EDF. And we proceed with the integration of some structural health analysis that the client already had with the data, satellite data, InSAR interferometry movement data, and some ancillary information available. These models can get as complicated as you like. The more complicated might be more complicated to run it, but you might get better outputs, and you might be able to make better decisions. So if we compare the traditional structural health monitoring with the tool we have developed, the traditional ways, the advantages is that it is a very well-established system. Quite often, there are instruments really very well developed, providing with real-time data, which satellite InSAR interferometry is not. It's a system designed according to legal requirements, and the staff is already trained. Meanwhile, for SSHM, our tool, the satellite one, the advantage is that it allows you, as I showed just before, to monitor countrywide areas. There are no health and safety concerns because everything is done using satellite imagery and from our offices. There is an integration with the 3D models provided by end users. The ground movement, this is very important. It allows us to record all the deformation series of specific assets, so we can go back to the past and being able to understand how the evolution of deformation has been happening and where the maximum strain might be concentrating within the asset. The downsides for both is, for the traditional one, is that, of course, you have health and safety concerns. It's very time-consuming to install in-situ instrumentation, sometimes to make sense of it, and so on. And for our tool is that, okay, this is a pioneering thing, and it is not yet known and understood, so staff training is required, and outputs only can be as good as the input data, which, not always we have very good input, a good BIM model or whatever it is. Sometimes we have to rewrite our 3D models anyway. So how does it work? So basically we are integrating and compiling 3 data sources: a master map, which is basically a digital representation of the terrain and the ground from different sources. Then we have a 3D or BIM information model of specific assets that we are going to be analyzing. And of course, the output of interferometric analysis, InSAR interferometry surface deformation. So we integrate those 3 layers, and we have developed an algorithm that goes through these 4 different phases: configuration, alignment, classification, and finally the test. So running the model to be able to visualize how the deformation of those specific assets have occurred in time. I'm not going to get too much into the details, but it's just important to highlight that we are configuring few things, and we are configuring the 3D models, we are configuring the InSAR data in relation to the 3D model, particularly for the position, the most precise position, the configuration also of the terrain model, and also, and quite important, we are doing a feature grouping in order to be able to classify later on in the process the InSAR interferometry data to allocate it to specific parts of the asset in the digital world or in the 3D model. And then after that, what we do is, at the end, we run the test. In this particular case, we have done the test, obviously, in the line of sight of the satellite, line of sight displacement analysis, time series analysis to see the evolution of the formation, and another complex tests. Tests can be run to, tests can be related to health condition, routine monitoring, but also for prediction of structural health. Here we have some examples of the project that we have done with EDF. A video, please. So basically, we create a RAG output in which, which tell us, a specific threshold that might be indicated by the end user. So we are able to kind of to fly through the location of a group of assets. The good thing is that obviously the satellite images are very big in size, so we are able to monitor multiple assets with only one data set or one image acquisition in time. And that allows us, as you can see, to depict where the deformation is occurring. So green is stability, yellow and reds are deformation. So this study, which was done in Canning Town and East India DLR station, show a quite important feature of subsidence that was ultimately related and also proven by TfL related to the construction of one of the stations for Crossrail. Yeah, next one. So the conclusions with TfL were that outputs provided an independent validation for this tool, this SSHM concept. The amber and red thresholds were exceeded between October 2013 and 2014. And also TfL identified some measurements with in-situ instrumentation that were in agreement with what it was measured by the system. We did the same for EDF in Hinkley Point A and B, and also C, although C is in construction, but it was very interesting to look at the change detection. It's a different technology. I'm not going to get into details today, but it allowed us as well to kind of perform this type of approaches in critical infrastructures like a nuclear power station. The conclusions with Hinkley Point A and B is that SSHM analysis was performed over the structures of A and B. Interesting as well because this site is covering the whole life cycle of a nuclear power station. We have A, decommissioning, B, which is stopping operations, and C, being built. The observations could not be validated because there were not, believe it or not, available local on-site measurement data. And what we could see is that part of the dewatering happening because of the construction of Hinkley Point C was starting to affect Hinkley Point B, which is just next door. So conclusions for this tool, this approach, is that remotely sense structural health monitoring is feasible according to our end users and according to ourselves as well. It provides high quality and reliable outputs on structural health as well as surrounding regions. It can be implemented without the need of in-situ instrumentation, although in-situ instrumentation will reinforce this type of approach. The more data that can be integrated to enrich SSHM, the better. The more meaningful will be the assessments and also the decisions for resilience for the infrastructure. And it can be used for SHM analysis of several assets in their environment, allowing resilience assessments for the whole infrastructure system, not only for independent assets. So what is next for us? Yeah, and this is quite important. I would like to introduce the project of 4C. We are now, with this tool, SSHM is going to develop towards predictions, but also all of the outputs from SHM, amongst other things that are going to be integrated in, as part of the project, will be ultimately the objective of 4C, which is to help and assess a resilient assessment for the end users. And this is just an example, a very quick example of what we are doing. So we looked at the asset itself, now we are looking at the surrounding areas in 4C. So we are looking at things like landslide modeling, in which we are integrating satellite-derived data, InSAR interferometry from the past, current, continuous monitoring, physical environment characteristics of the site, of course, the digital terrain model, as well as rainfall data and weather forecast, in order to, together with the University of Edinburgh and University of Canterbury, create this landslide modeling, which will help us in the GIS environment to predict potential landslides or subsidence or movements. So we are talking about two things: SSHM to monitor the assets, and for the environment, what is developed with the 4C project in a GIS environment. Thank you very much.